AP problem number 1 for chapter 16. This is what's called a weak acid equilibria problem. There are many of these problems. They work exactly like our equilibrium problems from chapter 15. There's going to be one added tweak to it, though. I want you to watch for it. I'll make it obvious when it happens. But there's going to be one thing we're going to do a little bit differently, and it's actually a good thing. Okay, so let's talk about weak acids. Weak acids are those things that, remember, do not 100% dissociate into the acid part, which is the hydronium ion, and the anion. That this happens at a very small percent compared to strong acids. Strong acids, 100%, very easy. There is no equilibrium with strong acids because they go to the right side 100%. Or as close to 100% as we can get. So we do not worry about equilibrium with strong acids, but with weak acids we have to, because there's a balance between how much of this stays put and how much of this forms this. And because it's not 100% to one way or the other, we have to calculate the equilibrium of it. So this says, write the equilibrium constant expression for the dissociation of HF in water. Now that is actually a pretty easy thing for us to do. I know you know how to do that. Excuse me, so let's just take a quick look at A. What would A be? Ka equals some number, but it also equals the concentration of H3O plus the hydronium ion and F minus the anion all over HF, the weak acid, like that. So that's the written expression for it. Now remember that this also has a value, and it's right here at 7.2 times 10 to the negative fourth. Okay, so here's what we're going to do. I'm going to erase this. Take a look at that. Actually, here, I'll move it up and out of the way so you can still see it, but I need to use this area here. There we go. Move it up like that, out of the way. Boom. Now, so here's our equilibrium part. We're going to start off with, and this says we're going to start off with 0.4 molarity. So 0.40 molarity here. This doesn't count. That's a pure. That doesn't change at all. So, and then of course we're going to start off with 0 and 0 because this is our ice. This is our ice chart. Okay, there's nothing different about this than anything we did in chapter 15. We're going to subtract some amount here because it's a reactant and it decreases in concentration. We're going to add some amount here because it's a product and increases in concentration for both of these. And because there's a 1 there and a 1 there, they're both 1x's. Now the equilibrium is simply moving all of this stuff down to 0.40 minus x like that, and this is x and this is x. So if I have this equation up here and I plug in the x's here for that and that, okay, all over 0.4 minus x like this equals 7.2 times 10 to the negative fourth. Now that's all the information we need to get this done. And what we end up doing is getting an x squared on top, and then on the bottom we get the 0.40 minus x, and then we have to multiply through. And let me tell you something. Do you see this part right here? The minus x. As it turns out, if we look at all of these Ka's, the Ka is just the equilibrium constant for an acid. That's all it means. So the Ka is nothing different than a regular K. This is specifically referring to a weak acid in this case. That's all it is. And if we had a weak base, it would be a Kb. That's it. So we're not dealing with this number. This 7.2 times 10 to the negative 4 still represents an equilibrium constant, which is the same thing we had in last chapter. So notice how small it is, times 10 to the negative fourth. That means that the reactants are heavily favored. Now let me explain what that means. If the reactants are heavily favored, that means that this 0.4 molar concentration is going to be a lot higher than whatever it loses. If reactants are heavily favored, the concentration of this is going to be much higher than the products. Okay, so if that's true, then all we have to do to make this problem a whole lot easier over here is just to ignore the minus x on the bottom. So I keep the x's on top and I square them like that. And then I simply make that equal to, and I move just the 0.40 molar over here, and now just simply multiply these two together, like that. So the Ka times the initial concentration, which makes this much, much easier. Here's why. Because I take the square root of both of these, like that, and that equals my x. So x squared, let's do that first here, actually. Let's move both of this down. Oh, yeah, that worked well. So let me do this, the calculation for this. Where's my phone at? All right, let me get out of my game I was playing. Now, so I just got 0.4 times 7.2 EE4 minus. Okay, that's going to equal, that's x squared equals 0.000288. I just wrote the whole thing down. I'm not worried about significant figures right now. And then I take the square root of that, and x equals 0.01697. And then there's like a 0 after that, so I'll just stop there. That makes it easy. Okay, so if I round this off, I get that. Look how easy this math was compared to doing the quadratic formula. How do you know if this is going to be, if this x up here is going to be small enough so that it does not matter? I'm sure that's what your question is. How do you know that? Okay, so here's what you do. First of all, I go back and I take my answer here, my 0.017, I square it and divide it by 0.4, and if I do that, I get exactly 7.2 times 10 to the negative fourth. Exactly. So that means that that x is not large enough to change it doesn't change anything. So that's one of the ways that you know. Another way is to look at this. If I take the Ka and divide it by the initial concentration of the acid like this, and if I get less than 5%, 5% is 0.05 like that. Okay, that means that if I have 7.2 times 10 to the negative fourth like this, divided by the initial concentration, there we go, of 0.04 like that, what does that equal? Let's find out. 7.2 EE4, I just deleted it. 7.2 EE4, nope, this is not working. E4 minus, there we go, equals that, divided by 0.4 equals. So what this equals is 0.0018. Nowhere close to 0.05, to 5%. This is called the 5% rule. You can use the 5% rule anytime the Ka divided by initial concentration of the acid is less than 5%, or 0.05. And it clearly is this time. Okay, so that means that getting back up to, I should go back up and take a look and make sure I've answered my question here. It says, calculate the molar concentration of H plus, or H3O plus, in a 0.4 molar hydrofluoric. So, okay, so this right here is my 0.017 molar, 0.017 molar. So this right here is the answer. X equals 0.017 molar. Okay, here's the next one coming up. The next one's a little bit more complicated. It's the second part to this problem.